Welcome to the deep dive. And before we jump into the actual material today, I was looking over the directory metadata for this session.
Oh, yeah.
Yeah, and it perfectly sets the stage for what we're going to be doing today. Like, if you were searching for this, the title you'd see is The Deep Dive, Decoding ISO 2047 and the Hidden Language of Computer Terminals.
That is quite the mouthful.
It is. But the description, it captures the essence of our source material perfectly. It reads, ever wonder what happens behind the screen when you hit backspace or hear a computer bell?
Right.
In this deep dive, we explore the fascinating, outdated world of ISO 2047, the 1975 standard for graphical representations of 7-bit control characters. From Teletype Model 33 quirks like WRU, Who Are You, to the obscure visual symbols used for debugging early tech, we unpack the hidden codes that built modern computing.
It really hits all the marks.
It does. And we've got all those target SEO keywords woven in there too. ISO 2047, computer control characters, 7-bit coded character set, tech history, Teletype Model 33, ASCII debugging, graphical representation of control characters, legacy computing, Unicode control pictures. The works.
Covering all the bases.
Exactly. But beyond the metadata, the core question we are exploring today is something most of us, well, we just never think about it.
We take it completely for granted.
We really do. When you, the listener, type on a keyboard today, the feedback loop it's instantaneous, it's visual.
Very tangible.
Right. You press the letter A, and a luminous A appears on your screen. But what happens when you press a key that tells the computer to do something completely invisible?
That's the million-dollar question for early computing.
How do you visualize a command that simply says, start a new line, or acknowledge this message?
You've hit on a fundamental problem of early computer engineering there. We are essentially talking about the translation of functional mechanics into a visual language.
Right.
And in the early days of computing, that translation was quite literal. I mean, you couldn't just trust that a machine received an invisible command.
You had to see it.
You often needed to prove it physically. Yes.
And that necessity is exactly what brings us to our sole source for today's discussion. It's a Wikipedia article detailing ASO 2047.
Which is an incredibly dense read.
Oh, it is not a narrative at all. If you pull up this article, it is just a dense, incredibly bureaucratic table.
Just a wall of text.
A wall of acronyms, hexadecimal codes, and geometric shapes that honestly, they look like alien hieroglyphs.
They really do.
But the premise here is that this dry table is actually a blueprint of early digital communication. It's a catalog of invisible forces.
That's a great way to put it.
So to start at the absolute foundation here, what exactly was ISO 2047 trying to solve back in 1975?
Well, to understand the solution, you really have to understand the specific hardware environment of the mid-1970s.
Okay, set the scene for us.
We're talking about the era of terminals, specifically video display terminals, or VDTs, and their electromechanical predecessors, like teleprinters.
The loud, clunky machines.
Exactly. So ISO 2047, which was published by the International Organization for Standardization, is formally titled Information Processing Graphical Representations for the Control Characters of the 7-bit Coded Character Set.
Quite the title.
Very dry. But its entire purpose was to assign a printable, visible picture to a command that is inherently unprintable.
But why? I mean, why would you want to print an unprintable command? If I press backspace, I want the cursor to move backward.
Right.
I don't want a picture of a backspace to appear on my screen.
And normally, yes, you wouldn't. But think about what happens when something breaks.
Okay.
Imagine you are a systems engineer in 1975. You've got this massive mainframe in one room, and it's communicating with a terminal down the hall over a noisy analog telephone line.
So lots of static, lots of potential for errors.
Endless potential for errors. The terminal keeps crashing or printing garbage characters. You need to look at the raw stream of data coming over that wire to see what the mainframe is actually sending.
Right, so you put it in a diagnostic mode.
Exactly. But here's the catch. If you just send the raw data stream to the terminal to display, the terminal's hardware is just going to interpret those control characters.
Oh, I see.
If the mainframe accidentally sends a clear screen command because of line noise, your terminal clears the screen.
So you lose the very evidence you were trying to examine.
You lose the evidence. So engineers built a monitor mode or a transparent mode into these terminals.
How does that work?
In this mode, the terminal's character generator, the internal circuitry that maps a binary code to a pattern of pixels on a screen or pins on a print head, It bypasses its normal instructions.
It stops obeying the commands.
Right. Instead of executing the control character, it looks up a special table and draws a symbol on the screen representing that character.
Oh.
And ISO 2047 was the international agreement on what those specific symbols should look like. It also established standard two-letter abbreviations for every single command.
Just to ensure there was zero ambiguity when engineers were talking to each other.
Precisely. No guessing involved.
It's kind of the equivalent of a mechanic taking the cover off an engine to watch the valves move rather than just listening to the car run. You have to expose those hidden mechanics.
That's a perfect analogy.
But the source material indicates this didn't just spring out of nowhere in 1975. The timeline in the article shows a much deeper lineage.
Right, it does. Standardizing a global visual language takes a lot of time.
I can imagine.
The Wikipedia text explicitly notes that the graphics and the two-letter codes formalized in ISO 2047 were essentially carried over, completely unchanged, from much older standards.
Really? How old?
The primary ancestors are a European standard from 1968 known as ASCII 17 and an American standard from 1973 called ANSI X3.32.
1968. Let's just ground ourselves in that year for a second.
It's early.
That is incredibly early in the timeline of widespread data communication. We are talking about the Apollo program era here.
Yes.
The fact that the European Computer Manufacturers Association, ECM, was already recognizing the need to draw pictures of network control codes in 1968.
Yeah.
I mean, that tells me data networks were already getting way too complex to troubleshoot by merely guessing what was going wrong.
Oh, the complexity was scaling incredibly rapidly. In the late 1960s, you were transitioning from isolated mainframes running batch jobs to time-sharing systems.
Where multiple users are accessing a central computer at the same time.
Exactly. Via remote terminals, you suddenly had data streams intermingling, complex routing codes, and constant communication handshakes.
The margin for error must have been high.
Very high. And the cost of computer time was astronomical back then. If a batch job failed because a single control character was corrupted, you wasted thousands of dollars.
Wow.
Establishing a unified diagnostic language wasn't just an academic exercise for these guys. It was an economic necessity.
And that necessity clearly resonated globally, because the article lists the different national adoptions of this standard, and it kind of reads like a roll call of the emerging tech powers of the late 20th century.
It really does.
It mentions the standard was adopted in China as GBT 3911 1983. In Korea, it was KSX 1010, which the source notes was formerly known as KSC 5713. And in Japan, it became JISX 0209 in 1976.
That geographical spread is crucial to understand. Computing was ceasing to be purely an American or European domain.
Right.
For an IBM mainframe in New York to eventually communicate with a terminal in Tokyo, the foundational layers of how data was structured and how errors were visualized had to be identical.
It's the digital equivalent of agreeing on international maritime flags.
Exactly. A universal language for ships passing in the night, or in this case, packets of data.
But there's a specific detail about that Japanese standard in the source that really caught my eye. It says JISX 0209.1976 was officially abolished on January 2010.
January 2010.
That is quite a late date for something rooted in 1960s terminal debugging.
It is incredibly late.
Right. I mean, by 2010, the iPhone had been out for 3 years. We were firmly in the era of high-definition touchscreens and cloud computing. Yet somewhere in the Japanese industrial standards bureaucracy, a committee finally looked at a document detailing how to draw tiny geometric shapes for 7-bit teleprinter codes and decided, yep, it's finally time to take this off the books.
It speaks volumes about the concept of technical debt and just the sheer inertia of infrastructure standards.
Once it's in print, it stays in print.
Well, when a standard is embedded into the firmware of millions of devices worldwide, you can't just unpublish it because it feels old.
Good point.
There might be a shipping company or a banking backend somewhere still utilizing a legacy system that references that specific 1976 document for compliance.
Right, some dusty server rack in a basement.
Exactly. Standards bodies are notoriously conservative, and rightly so. They only abolish a standard when they are absolutely certain its removal won't cause a catastrophic ripple effect in legacy systems.
So, if the Japanese standard was abolished in 2010, and the source notes that the graphical symbols of ISO 2047 are generally considered outdated and rare today, what replaced them?
That's a great question.
If a programmer today needs to look at a raw data stream and spot an invisible control character, how do they do it without these specific geometric symbols?
The need to debug data streams definitely hasn't gone away. but our displays are no longer constrained by low-resolution character generators.
We have millions of pixels now.
Right. Modern tools typically rely on text-based representations. The source mentions two common methods. First, the ASCII 646 three-letter abbreviations.
Okay, what does that look like?
So instead of drawing a strange symbol for the escape command, a modern text editor in debug mode will simply display the letters ESC in a little colored box.
Oh, that makes total sense. It's
Yeah.
much more readable for a modern programmer than trying to memorize abstract shapes.
Precisely. You don't have to consult a manual to know what ESC means.
Yeah.
The other common method mentioned is caret notation.
Caret notation.
Yes. This is highly prevalent in Unix and Linux environments. You use an upward-pointing caret symbol followed by a letter.
I've seen that.
For instance, the escape character, which is the 27th character in the ASCII table, is represented as caret bracket. A line feed is caret J.
Caret.
It's a shorthand that maps the invisible control codes to the visible alphabetical keys on a standard keyboard.
So we traded custom geometry for practical typography.
We did. It's much more efficient.
But for the duration of this deep dive, I want us to live in that era of custom geometry. I want to look closely at the logic of these glyphs, because they are an incredible window into how engineers conceptualized data when data was still a very new concept.
It's a fascinating way to look at it.
Let's look at the very first entry in the standards table. Hexadecimal 00.
Hex 00, the very bottom of the 7-bit architecture.
A common abbreviation is NUL. The full name is simply null.
Yes.
Now, the concept of null is philosophically interesting before you even get to the computing part.
Very true.
It's not a space. A space is a tangible thing. It moves the cursor forward. Null is the absolute absence of value. But how did that actually function in early hardware?
Well, in the context of the early punched paper tape systems, which were heavily used for data storage and terminal input, null was incredibly literal.
Literally nothing.
Exactly. A paper tape represents data by punching holes in a row. A 7-bit code meant there were 7 possible positions for a hole across the width of the tape.
Okay, I'm picturing that.
For the NUL character, the punch mechanism simply didn't fire. A row with absolutely 0 holes punched in it was a null.
So it's just blank tape.
Just blank tape.
Why would you need to send blank tape? What's the point of sending nothing?
Primarily for mechanical timing.
Mechanical timing.
Remember, these were heavy physical machines. If a command told the teleprinter's heavy metal carriage to return to the left margin, that physical movement took a fraction of a second.
Because it's a heavy piece of metal flying across the machine.
Right. If the computer kept sending text data during that fraction of a second, the letters would print randomly across the paper as the carriage was flying backwards.
Oh, wow. It would just streak across the page.
It would be a mess. So the computer would send the carriage return command and then immediately send a stream of null characters.
I see.
The tape reader would read the blank tape, do absolutely nothing, and effectively buy time for the mechanical carriage to finish its journey. Null was a digital pause button.
That's a brilliant way to frame it. A digital pause button.
Yeah.
But here is the challenge for the ISO 2047 committee. How do you draw a picture of a pause button?
It's a paradox.
How do you visualize nothingness? According to the table, the official symbol they chose for NUL is a tiny, empty box, U plus 2395 in modern Unicode. And the official 2-letter abbreviation is NU.
An empty box is a very pragmatic solution, really.
Yeah.
If you want to show that a character space is occupied by a command that does nothing, you have to provide a boundary for that nothingness.
Right, because otherwise it's just blank space on the printout.
Exactly. If they just left it blank, the debugging engineer wouldn't know if the system received a null, a space, or if the printer simply dropped a character due to a fault.
That distinction is critical when you're debugging.
It is. The empty frame proves the character was successfully received and categorized as empty.
It's proof of absence. That's so clever. But standardizing these symbols wasn't always a clean, logical process.
Far from it.
We see evidence in the source that there was friction and debate over how to represent certain concepts. There's a very specific, almost tedious footnote regarding the character at Hex05. The inquiry character.
Yes. ENQ.
The common abbreviation is ENQ, and its primary visual glyph in ISO 2047 is a cross shape. It looks very similar to a Maltese cross.
That's right.
But the footnote points out that the standard also provides a fallback glyph. If you couldn't draw the cross, you were allowed to use a box with an X inside it.
Yes.
And here's the fascinating historical wrinkle. The older 1968 European standard, Irene 17, only listed that boxed X. It didn't feature the cross shape at all.
That seemingly minor detail is actually a massive clue about how standard-setting bodies function. Between 1968 in Europe and 1975 on the global stage, a debate occurred.
But why do you think they felt the need to change it? A boxed X seems perfectly clear. It means, hey, look here.
We have to speculate slightly based on the hardware constraints of the time, but the most likely culprit is visual clarity on low-resolution displays.
Visual clarity.
Think about it. A boxed X requires drawing a square and then drawing diagonal lines through it.
Yeah.
On an early dot matrix screen, which might only use a 5-pixel by 7-pixel grid for a single character, drawing a box with an X in it often results in a solid, unreadable smudge.
Oh, because the pixels just bleed together.
Exactly. You don't have enough resolution to render the distinct lines. A distinct cross shape, however, requires fewer pixels and relies on stark horizontal and vertical lines.
Which CRT monitors handled much better.
Much better. It's just easier to draw on a primitive screen.
So the global committee probably realized the European design was too complex for cheap hardware.
Right.
But they couldn't just delete it.
They couldn't. You can't just invalidate the older European standard entirely because there was already hardware out in the field manufactured between 1968 and 1975 that used the boxed X in its ROM chips.
So you'd break compatibility if you just erased it.
Exactly. So the ISO committee compromises. They promote the clearer cross shape to the primary status, but they enshrine the boxed X as an official fallback to ensure backward compatibility.
That's amazing.
It's a bureaucratic fossil preserved right there in the standard.
It really emphasizes that these aren't laws of physics we're looking at. They are human agreements, subject to all the messy realities of hardware manufacturing and committee negotiations.
Completely.
Let's move deeper into the table. If null is about nothingness, the next cluster of characters we see is intensely structural. I look at this block of codes and I see the absolute necessity for rigidity in early networking.
We're talking about hex V1 through hex 04 now.
Exactly. Let's look at those.
These are the communication control characters. They manage the flow and structure of the data payload. At hex R1, we have SOH, or start of heading.
Start of heading.
Hex 02 is STX, start of text. Hex 03 is ETX, end of text. And hex 04 is EOT, end of transmission.
When I see these, I immediately think of how we use the internet today. If I send an email, I just type the message, hit send, and I never think about how it gets there.
It's seamless for the user today.
But these codes suggest that in the 1970s, the application, or even the programmer, had to manually build the envelope for the data.
That's a very accurate analogy, building the envelope. In early network topologies, data didn't flow in a continuous, unstructured stream. It had to be meticulously packetized.
Every piece had its place.
Exactly. The start of heading SOH character acted as a loud announcement to every switch and router on the network. It essentially said, attention, the data following this character is not the message itself. It is routing information.
Like the address on the outside of the envelope.
Exactly. It contains the address of the destination terminal.
So the machines would read the heading to figure out where to send the data, and then they would encounter the STX, the start of text character.
Precisely. STX told the receiving machine, the routing information is over. Everything from here on out is the actual payload you need to print or display for the human operator.
The actual letter inside the envelope.
Right. And this would continue until the machine received ETX, the end of text character, which closed the payload.
And finally, EOT, end of transmission, which I imagine was the definitive sign-off, like, I'm dropping the connection now.
Yes, EOT was the command to disconnect the circuit entirely. Hang up the phone, basically.
Visually, the ISO 2047 symbols for these four are quite clever. I'm looking at them here. SOH, the start of the heading, looks like the top left corner of a box.
Yes.
STX is an upside-down T. ETX, the end of the text, is the bottom right corner of a box. You can literally see the visual framing of the data packet.
It's very architectural. The geometric shapes provide a distinct visual boundary when reviewing a diagnostic printout. You can see the start and end of the blocks at a glance.
It's all very rigid and mathematical. But nested right next to these structural commands is my absolute favorite detail of this entire Wikipedia article.
Oh, I know what you're going to say.
It completely shatters that cold mathematical feeling and injects a bizarre sense of human conversation into the network. It involves that inquiry character we were just discussing, the one with the cross and the boxed X at hex 05.
It is a striking historical note.
According to the source, if you were sitting at a Teletype Model 33, which was arguably the most iconic and ubiquitous terminal of the era, the physical key on the keyboard for this inquiry command wasn't labeled E and Q.
No, it wasn't.
It was labeled WRU. And the article helpfully translates that for us. WRU stood for Who Are You?
Who are you? It is a direct, literal translation of what the network handshake protocol was attempting to achieve.
I find that endlessly fascinating. I'm imagining a computer operator in a noisy room needing to verify a connection to a terminal in another city. They don't run a diagnostic script. They reach out and press a physical button that asks the machine on the other end of the telephone wire, "Who are you?"
It's very personal.
It is. It is an interrogation happening over copper wires.
To understand why this was necessary, you really have to understand the lack of security and certainty in early dial-up networks like the telex system.
It was basically the Wild West.
It really was. You were literally dialing a phone number to connect your terminal to another terminal. There were no digital certificates. There was no cryptographic authentication.
That's a phone connection.
Right. If you dialed a wrong digit, or if the telephone exchange misrouted your call, you might connect to a terminal in a completely different company.
And if you just started transmitting a sensitive financial report right away, you've just committed a massive data breach.
Exactly. You've just handed your secrets to a stranger. So standard operating procedure dictated that before you sent any payload, you pressed the WRU key. This sent the E and Q character down the line.
And what happens on the other side?
The receiving teletype, upon receiving an E and Q, was hardwired to respond. It didn't require human intervention on the receiving end at all.
Oh, so the person on the other end didn't have to type, "I am Terminal 5."
No. Inside the receiving teletype was a mechanical component called an answer-back drum.
An answer-back drum. A physical drum.
Yes. It was a literal rotating cylinder with rows of small metal pegs.
Like a music box.
Exactly like a music box. When the machine was installed, a technician would physically break off specific pegs to encode the machine's unique identifier.
So they programmed it with pliers.
Literally. They'd encode perhaps a company abbreviation and a terminal number. When the E and Q signal arrived, it triggered a solenoid that spun this drum.
And as it spun?
As the drum spun, the remaining pegs tripped contacts that transmitted that unique identifier back down the phone line.
That is incredible. So the receiving machine physically played its own name back across the wire.
That is exactly how it functioned. And the operator sitting at the transmitting terminal would see that unique identifier print out on their own paper roll.
And if it matches?
If it matched the machine they intended to reach, they knew it was safe to transmit the STX and the payload. Who Are You? Was a fundamental security protocol built out of spinning metal and solenoids.
It's just so tactile. And it makes you view modern networking through a completely different lens.
It really does.
When I open a web browser and connect to my bank, there is an immense amount of cryptographic handshaking happening in milliseconds. TLS certificates are being verified, public keys are being exchanged. But conceptually, at the very bottom of the stack, my laptop is still just walking up to the bank server and asking, "Who are you?" and demanding proof.
The fundamentals haven't changed.
We just automated the music box drum.
It is the exact same paradigm, just abstracted behind millions of lines of code. The Teletype Model 33 just made it wonderfully explicit for the human operator.
Well, since we are talking about spinning drums and solenoids, let's lean into that.
Yeah.
Because as abstract as Start of Heading is, the reality is that many of these 7-bit codes were designed to control heavy physical machinery.
Very heavy.
And what's wild is how much of that physical vocabulary has survived into our modern glass screen era. Let's look at Hex 07. The common abbreviation is BEL.
The full name is bell. And in 1975, that wasn't a metaphor. It was a literal command to ring a bell.
Explain the use case for that. I mean, why does a computer need to ring a bell?
Remember that early data processing often involved long periods of waiting? An operator might start a batch job that takes 2 hours to compile on the mainframe.
Right.
They aren't going to sit and stare at a silent terminal for 2 hours. They might be in the next room sorting punch cards or getting a coffee.
Does he need an alert?
The mainframe needed a way to alert the operator when the job was done, or, more importantly, when the job encountered a fatal error and halted.
So it sends a BEL character down the wire.
Yes. Upon receiving Hex 07, the terminal would trigger a circuit that rang an actual 110-volt mechanical bell inside the casing.
Like a fire alarm?
Essentially. It was an audible alarm built directly into the text stream. You could embed BEL characters into your code so the machine would literally chime when it reached certain milestones.
The ISO 2047 symbol for it is great too. In modern Unicode, it's U+237E, and it looks a bit like an old-fashioned hotel desk bell with little vibration lines coming off it.
It's a very charming glyph.
But the physical control goes far beyond just making noise. It dictates the entire geometry of how text was laid out on paper. I'm looking at the list of format effectors.
Ah, the format effectors.
At Hexo 8, we have BS, backspace, HT at Hexo 9, horizontal tabulation, LF at Hex 0A, line feed, VT at Hex 0B, vertical tabulation, FF at Hex 0C, form feed, and CR at Hex 0D, carriage return.
These commands are direct descendants of the mechanical typewriter. A computer screen today can place a character anywhere instantly using coordinate geometry.
Just light up a pixel.
Exactly. But a teleprinter operates under strict physical laws. The printhead is a heavy block of metal. It moves sequentially left to right. The paper feeds linearly from a roll or a stack.
Let's break down the distinction between carriage return and line feed. Because I think a lot of people today use the enter or return key on their keyboard and assume it's one single action. Just go to the next line.
It feels like one action to us now.
But historically, it was two very distinct physical movements.
It's a crucial distinction. Carriage return, Hex 0D, specifically commanded the heavy printing mechanism, the carriage, to slide all the way back to the left margin.
Just horizontal movement.
Yes, but it did not move the paper. If you only sent a carriage return, the next line of text would print directly on top of the previous line.
Oh, man. So you just get an illegible black smudge of ink.
Exactly. You're just striking the same piece of paper over and over.
So you needed a line feed, Hex 0A.
Yes. Line feed commanded the platen, the roller holding the paper, to rotate exactly one notch, advancing the paper up by one line.
Vertical movement.
Therefore, to start a new line of text correctly, the computer had to transmit both characters, a carriage return to move left and a line feed to move down, often abbreviated as CRLF.
CRLF. And the ghost of that physical necessity still haunts us today.
It does. It causes headaches even now.
It is the reason why, for decades, text files created on a Windows machine looked broken when opened on a Unix or Linux machine, and vice versa.
The great new line format war.
Because Windows operating systems historically used the two-character CRLF sequence to mark a new line, mimicking the physical teleprinter.
While Unix-based systems decided that was inefficient.
Right. They just used a single line feed character to represent a new line. We had a digital format war purely because of the ghost of a 1960s mechanical carriage.
It is the ultimate example of skeuomorphism. We retained the data structure of the physical mechanism long after the mechanism itself was replaced by pixels on a screen.
But visualizing these physical movements for the purpose of debugging proved to be incredibly tricky for the ISO committee.
Very tricky.
The standard really seems to struggle when it comes to the backspace character. Let's look at the footnotes for Hex 08.
The problem with backspace is representing kinetic energy in a static single character space.
Right, because the command means move the printhead one position to the left.
Which is easy to do mechanically, but hard to draw if you can only take up one space on the grid.
Exactly. The footnote in the standard acknowledges this difficulty. It states that a best fit approximation must be used. Its primary suggestion is an arrow pointing to the upper left.
Okay.
But then the source lists an entire array of alternative, defensible choices. It suggests hooked arrows, arrows that curve back on themselves in a U-turn shape, arrows with a right-angle bend pointing left, arrows curving downwards and leftwards.
It's almost comical. They're throwing every possible curved line at the problem.
Why was a simple straight arrow pointing left not good enough?
Because a simple straight arrow pointing left is already a standard typographical and mathematical symbol.
Oh, like the lesson sign.
Or just a general directional indicator. It could be confused for a logical operator depending on the context of the code. The debugging engineer needed to see a symbol that instantly conveyed the action of the mechanism retreating against the normal flow of text.
So the hooked and looping arrows attempt to visually communicate a reversal of momentum.
Exactly. Graphic design under extreme constraints.
But if we are talking about extreme physical actions, we have to look at the device controls. This is the section of the table encompassing DC1 through DC4, occupying hex codes 11 through 14.
These are arguably the most raw physical commands in the entire standard.
Why do you say that?
Well, the names are deliberately generic. Device Control 1, Device Control 2, and so on. They were designed as wildcards. The standard didn't mandate what they did. It just provided the codes so that hardware manufacturers could wire them to turn specific peripheral devices on and off.
And the Wikipedia article gives us a vivid example of how they were actually used in practice, returning to our favorite machine, the Teletype Model 33. It explains exactly what these generic controls triggered on that specific hardware.
Yes, on the Model 33, these controls manage the physical paper tape system.
The paper tape.
A teleprinter wasn't just a keyboard and a printer, it often had a separate paper tape puncher and a paper tape reader bolted to the side of it.
Like a massive attachment.
Right. This allowed you to record data offline and then transmit it later at maximum speed.
And the device controls manipulated those peripherals. The source notes that DC2 and DC4 were commonly mapped to the puncher. DC2 was labeled Tape E, and DC4 was labeled with an abbreviation that effectively meant not Tape E or Tape Off.
Consider the reality of that. You are a terminal receiving a quiet stream of data. Suddenly, the invisible DC2 code arrives over the wire.
Tape E up?
Immediately, a heavy electrical motor engages. A complex mechanism of hardened steel pins begins violently punching holes into a thick strip of paper tape at 10 characters a second.
It must have been so loud.
It is loud, it generates heat, and it creates literal physical confetti. It continues this industrial process until the DC4 command arrives and the motor abruptly shuts off.
The computer is reaching across the country and physically turning heavy machinery on and off in your office.
It's a very visceral form of remote control.
And the source also mentions DC1 and DC3.
Yes. DC1 and DC3 were mapped to the paper tape reader. DC1 was commonly referred to as XON and DC3 as XOF.
XON and XOF.
If you wanted the terminal to start transmitting the data that was stored on a punched tape, you sent the DC1 command. A motor would engage, physical star wheels would pull the tape over a reading head, and the terminal would start sending data based on the holes it sensed. DC3 would halt the reader.
This XON-XOF concept became a massive part of computer history, didn't it?
A huge part.
It evolved from physically stopping a paper tape motor into a broader software concept called flow control.
Exactly right.
If a computer was receiving data faster than it could process it, it would send an XOFS command to tell the sender to pause. Once it caught up, it sent XON to resume. We abstracted the physical paper tape motor into a software buffer limit.
It is another instance of physical reality mapping directly into software architecture. And the visual symbols assigned to these 4 device controls in ISO 2047 are wonderfully abstract, yet somehow fitting for industrial machinery.
What do they look like?
They are represented by circles with different quadrants filled in or shaded. DC1 has the top left shaded, DC2 has the top half shaded, and so on.
Oh, interesting.
They resemble the phases of the moon, or perhaps more aptly, the rotating cams and gears inside the machinery they controlled.
It's an industrial aesthetic for an industrial function. But eventually, the machines had to do more than just punch tape and ring bells. They had to manage the complexity of the data itself.
Right. The logic of the network.
Let's move to a group of characters that I think of as the bureaucracy of the network. Because once you have machines talking to machines without humans intervening, you need an automated way to manage disputes, confirm receipts, and organize the paperwork.
This is where we see the true foundation of network protocols. The core of this bureaucracy rests on the acknowledgement characters.
Let's look at those.
At hex 06, we find ACK, standing for acknowledge, and at hex 15, we have NA, negative acknowledge.
I love how straightforward these are. The visual symbols chosen for ISO 2047 are universally understood. The symbol for ACK is a literal checkmark.
Simple and effective.
Just a simple graphic indicating, yes, the data was received and the checksum is correct. The symbol for NAC is the same checkmark, but with a horizontal line struck forcefully through it.
A visual veto.
Exactly. A visual, no, the data is corrupted, please send it again. It's like grading a test.
The elegance is in the simplicity. Early data transmission over analog telephone lines was incredibly prone to errors. Static on the line would frequently flip a bit from a 0 to a 1, turning an A into a B, or worse, turning an A into an end of transmission command.
Which would just terminate the whole session.
Right. So data was sent in blocks. A transmitting machine would send a block of text, followed by an ETC character hex 17 end of transmission block.
And then it would just wait.
Exactly. It would pause and wait for the receiving machine to process the block. The receiver would calculate a checksum mathematically to verify the data's integrity.
And if it's good,
If the math checked out, it transmitted an ACK back down the line. The sender, upon receiving the ACK, would proceed to send the next block.
and if it's bad.
If the receiver detected an error, it sent an AK. The sender would then rewind and retransmit that same block. It is a highly choreographed, continuous loop of verification.
And intertwined with that process is SYN at hex 16. Synchronization. What was the role of that character?
SYN was essential for synchronous transmission systems. In simpler asynchronous systems, like standard dial-up modems, every individual character was framed by a start bit and a stop bit to tell the receiver when to read.
Start reading, stop reading.
Right. But that added a lot of overhead. Synchronous systems transmitted data in a continuous rapid stream without start and stop bits. To make that work, the transmitter and receiver clocks had to be perfectly locked in time with each other.
Like two musicians keeping the same beat.
Precisely. Before transmitting the actual data, the sender would stream a continuous series of SYN characters.
SYN, SYN, SYN.
The receiving hardware would lock onto the repeating bit pattern of the SYN character and adjust its internal clock to match the incoming signal exactly. Once they were synchronized, the data payload could flow seamlessly.
Okay, so we have the check marks for success, the crossed out check marks for failure, and the synchronization beats to keep time. But what happens when the bureaucracy fails entirely? What happens when a machine is hopelessly confused or a process needs to be violently aborted?
That's when you hit the panic buttons.
We have panic button characters.
The most direct panic button is canon at hex 18, cancel.
And what does that look like?
Its symbol in ISO 2047 is a stark geometric shape. It resembles an hourglass or two triangles touching at their points.
What triggers a cancel command?
Can was generally used to tell the receiving system to completely discard the data it had just received in the current block, usually because the transmitting system itself realized it had made an error, or the human operator hit an abort sequence.
So it just trashes the current block.
It's a command to wipe the slate clean for the current operation without dropping the connection entirely.
And then there's SUB at hex 1A, substitute character. The standard dictates its visual symbol looks like a little blot containing a question mark shape, or perhaps a reversed S. Why would a machine need to substitute a character?
The substitute character was a crucial mechanism for graceful failure.
Graceful failure, I like that term.
Imagine a terminal receiving a stream of text, and one specific byte is garbled by line noise so badly that the terminal's hardware simply doesn't recognize it as any valid character in the 7-bit set.
It's just junk data.
Right. Older, less sophisticated hardware might simply crash or hang indefinitely when it encountered an illegal instruction.
Which is catastrophic if you were in the middle of a large job.
Exactly. So more advanced hardware was programmed to catch that error. Instead of crashing, it would say, I received an unreadable byte. I will discard it, and in its place on the screen or printout, I will insert the SEB character.
Oh, I see.
It was a visible placeholder that told the human operator something was supposed to be here, but it was lost in transit. It allowed the rest of the transmission to continue uninterrupted while flagging the specific point of failure.
It's a managed failure state. I don't know what this is, but I'm not going to let it ruin the whole document.
That is very smart engineering.
It's pragmatic.
But if we are talking about smart engineering, we cannot talk about this standard without bowing down to hex 1B, ESC, escape.
Yes, escape. Represented in ISO 2047 by a circle with a horizontal line drawn through the middle of it. U+238B in modern Unicode. It is arguably one of the most powerful and significant control characters ever devised.
Why is it so powerful? In modern computing, I hit the S key to close a full-screen video or cancel out of a dialog box. It feels like a very mundane go-away button. But historically, it was much more than that.
The clue is in the name. Escape. It is an escape from the limitations of the 7-bit architecture.
What do you mean? You have to remember the fundamental constraint these engineers were working under. A 7-bit code only allows for 128 unique values total.
Just 128.
That includes all your uppercase letters, lowercase letters, numbers, punctuation, and all 32 of these control characters we've been discussing.
That leaves absolutely zero room for anything else.
Exactly. What if you want to tell the terminal to change the text color to red, or clear the screen, or move the cursor to coordinate line 10, column 20? You don't have any unique 7-bit codes left to assign to those complex commands. You've run out of numbers.
So how does escape fix that?
The escape character fundamentally alters the state machine of the receiving terminal. It acts as a massive modifier key. When a terminal receives the ESC character, it essentially stops treating the incoming data as normal text.
It shifts gears.
It says, okay, the very next characters I receive are not letters to be printed. They are part of a special extended command sequence.
So you string characters together to make new commands.
Precisely. These became known as ANSI escape sequences. For example, if the terminal received an A, it would print A. But if it received the ESC character, followed immediately by an open bracket, followed by the letter A, the terminal wouldn't print anything.
What would it do?
It would interpret that specific multi-character sequence as a command to move the cursor up one line.
That's brilliant.
By utilizing escape as a gateway, engineers essentially unlocked an infinite number of command combinations without needing to expand the underlying 7-bit architecture. It allowed hardware to evolve incredibly complex graphical interfaces over rudimentary connections.
It was a trapdoor built into the foundation that allowed the entire system to scale. The foresight to include that in the standard is just staggering.
It saved the computing industry from locking itself into a dead end.
Before we leave the bureaucracy section, though, I want to look at how they organized information itself before the era of visual operating systems. We have 4 specific characters at the end of the 10 series hex codes: FS, GS, RS, and US.
The information separators, hex 1C through 1F.
Now, if I'm a listener sitting here at my laptop, I organize my digital life very visually. I have a desktop. I open a folder called Finances. Inside that, a subfolder called 2026. Inside that, a spreadsheet file. And in that file, I have rows and columns of data.
It's all spatially organized?
I can see the hierarchy instantly. How did engineers manage that kind of hierarchical data structure in a linear stream of 7-bit text?
They managed it precisely by using those 4 invisible separators. They are the primitive structural ancestors of your folders and files.
Okay, walk me through it.
You have to imagine data being written sequentially onto a massive reel of magnetic tape. There are no visual folders on a tape. It is just a million miles of ones and zeros. To make sense of it, a database program needs markers embedded directly into the text stream to define the boundaries of the data.
So how did the hierarchy work? Which one is the smallest?
It started from the smallest element and built upwards. US, at hex 1F, is the unit separator. A unit might be the smallest discrete piece of information, for example, a person's first name. You would separate the first name from the last name using a US character.
Like the comma in a modern CSV file.
Exactly like that. The next level up is RS, the record separator at hex 1E. A record is a collection of units. So a complete mailing address, name, street, city, zip might constitute one record. You use an RS character to separate one person's full address from the next person's address.
And it scales up from there.
Yes. Next is GS, the group separator at hex 1D. You might group thousands of individual records by geographical region. A GS character would mark the end of the East Coast group and the beginning of the West Coast group.
And the biggest one.
Finally, at the top of the hierarchy is FS, the file separator at hex 1C. This would separate entirely distinct data sets on the same magnetic tape, like separating the payroll database from the inventory database.
So a program parsing the tape would just scan for these invisible characters to understand the structure of the data it was reading.
Yes, it just look for those markers.
The visual symbols designed for these in ISO 2047 are brilliantly logical too. I'm looking at them. They are all U-shapes or squares divided into 4 quadrants.
They bill them in each other.
For the highest level, file separator FS, the top left quadrant is filled. For group separator GS, it moves to the top right. For record separator RS, the bottom right. And for unit separator US, the bottom left.
It's a progression.
It's a visual representation of moving sequentially through the layers of the hierarchy. It was a very elegant graphic design for something designed to be purely utilitarian.
It demonstrates a deep intentionality. They weren't just picking random shapes. They were building a visual syntax. Which brings us to the final and perhaps most intriguing aspects of the source material. We need to look at the anomalies, the edge cases, and the eventual afterlife of this visual syntax.
Let's start with the bookends of the entire ASCII table. We've talked extensively about the control characters clustered at the lower end of the hex values. But nested in this standard are 2 other crucial non-printing entities that sit outside that main block. At hex 20, immediately following the control characters, we have SP.
Space, the most ubiquitous invisible character in all of computing.
We press the spacebar more than any other key. It is the character we use to separate words and make human language readable. But in the context of ISO 2047 and terminal debugging, the space presents a unique problem.
The problem is ambiguity. On a normal printout, a space is just blank paper. But if you are an engineer examining a diagnostic dump and you see a blank area between 2 words, you have to ask yourself a critical question.
Did it mean to do that?
Right. Did the computer intentionally transmit a space character hex 20, or did the printer hardware simply fail to fire for a millisecond, leaving a gap?
You can't debug based on assumptions. You need proof.
Precisely. Therefore, in this diagnostic mode, you have to force the invisible space to become visible. You have to draw a picture of a space. ISO 2047 assigned it a very specific symbol, a tiny open triangle pointing upwards. In Unicode, it is U plus 25B3.
I'm trying to visualize reading a diagnostic printout where every single space between every single word is represented by a tiny upward-pointing triangle. It would look like an incredibly dense alien text.
It would be visually chaotic for a layperson, but for an engineer, it provided absolute certainty. Every triangle proved that a hex 20 code was successfully received and parsed.
And then at the absolute opposite end of the 7-bit table, far away from the control characters, sits hex 7F. The very last possible value, DEL, delete.
The delete character is historically fascinating because its very existence is tied entirely to the physical properties of punched paper tape.
More paper tape mechanics.
Yes. We've talked about how a null character, hex 00, is a row with absolutely 0 holes punched. The delete character, hex 7F, is the exact opposite. 7 bits means there are 7 possible hole positions. A value of 7F in hexadecimal translates to all 7 bits being set to 1. In binary, it is 11, 11, 11, 11.
So on a paper tape, a delete character is a row where every single possible hole is punched out.
Exactly. Now consider why that specific physical configuration was chosen for the concept of delete. Imagine you are an operator typing on a teletype and the machine is punching the tape as you type. You hit the wrong key, you've typed a B instead of an A. The physical hole for the B has already been punched through the paper.
You can't unpunch a hole. You can't put the paper confetti back in.
The physical error is permanent.
Right, so how do you fix it?
You press a physical button on the tape puncher that backspaces the tape one position, moving the erroneous B back under the punch bins. Then you press the rube out or delete key. The machine fires all 7 punch pins simultaneously, punching holes in every single position of that row. It physically obliterates the B by turning it into a row of 7 holes.
That is an incredibly clever mechanical hack. But how does the computer reading the tape know it's a mistake?
The software drivers running the tape readers were programmed with a very specific rule. If you read a row with all 7 holes punched, hex 7F, ignore it completely. Treat it as if it does not exist. Do not process it. Do not print it. Just move to the next row. It was a physical mechanism for erasing data by obliterating it with maximum entropy.
That is a brilliant piece of engineering history. And the visual symbol assigned to delete in ISO 2047 perfectly reflects that concept of physical obliteration. The standard dictates it should be represented by a shaded, cross-hatched block, a solid mass of ink that covers the entire character space. In Unicode, it's U plus 25A8, or similar. It looks exactly like a physical redaction in a classified document.
It is the visual representation of a void created by overwhelming presence.
But the implementation of these brilliant symbols wasn't universally smooth. The source material points us to a highly specific, curious anomaly regarding how this standard was adapted in certain environments. And I think this anomaly reveals more about the reality of early computing than the standard itself does.
You are referring to the note regarding the Irish standard.
Yes. The Wikipedia article references a document from December 13, 1995, titled Information Technology Irish 7-Bit Coded Character Sets. It's incredibly niche. But the source notes that in this particular Irish standard, the glyphs used for 4 specific control characters, ENQ, BS, CR, and SO, were considered anomalous. They did not match the shapes dictated by the global ISO 2047 standard.
And the reason provided in the text for this deviation is the critical part. It states the anomaly was possibly to accommodate the low resolution.
To accommodate the low resolution. That phrase just hits you with the stark reality of the hardware of the era.
It grounds the entire discussion. We have spent an hour marveling at the intellectual effort required to design these intricate, meaningful geometric symbols. The International Committee debated whether inquiry should be a cross or a boxed X. They agonized over how to draw a curved arrow that perfectly conveyed the kinetic reversal of a backspace. They designed elegant 4-quadrant squares for the information separators.
It built a perfect theoretical language.
But then, that perfect theoretical language collides with the gritty reality of cheap hardware. Think about the monitors of the late 70s and 80s. A standard CRT terminal didn't draw smooth vector graphics. It used a character generator ROM that mapped a character to a rigid, coarse grid of pixels, often just 5 pixels wide by 7 pixels high.
That's only 35 tiny dots to draw a complex shape.
Exactly. Try drawing the ISO standard for backspace, a sweeping, hooked arrow curving back on itself in a 5 by 7 grid. It's mathematically impossible to make it look smooth. The pixels just clump together. On the screen, it wouldn't look like an elegant arrow. It would look like an illegible, glowing smudge.
And if you are an engineer trying to debug a critical system failure, an illegible smudge is useless. You need clarity.
So, standard or no standard, local committees and hardware manufacturers had to bend the rules. The engineers writing the Irish standard, or whoever was manufacturing the terminals that standard was based on, likely realized the international ISO shape simply would not render legibly on the low-resolution cathode ray tubes or cheap dot matrix printers prevalent in their market. They had to choose simpler, blockier, perhaps cruder, anomalous shapes for those specific commands because the literal pixels required to draw the international standard did not exist on the screen.
It is the perfect example of high-level bureaucratic theory crashing headfirst into low-level physical constraints. The standard has to bend, or the system breaks. It's pragmatism over purity.
It is a poignant reminder of the incredible constraints under which early digital architects operated. Every single decision was a negotiation with hardware limitations.
So we know these symbols bent under the pressure of low resolution. We know from the earlier Japanese example that standard enforcement eventually aged out and was abolished in 2010. And the article itself plainly states that the graphical symbols of ISO 2047 are outdated and rare today, having been replaced by text abbreviations like ESC or caret notation. So are they just gone? Is this entire visual language lost to history, existing only in obsolete Wikipedia tables?
Fascinatingly, no, they are not gone. They have achieved a form of digital immortality. They have been preserved in amber within the ultimate arbiter of modern digital text. The source explicitly states that these specific visual symbols are preserved forever in the Unicode standard.
Unicode, the massive foundational system that ensures a text message sent from an Android phone in Brazil renders perfectly on an iPhone in Canada. The system that manages every human alphabet and every emoji.
Yes. The mandate of the Unicode Consortium is essentially to catalog and standardize every single character from every human language, past and present. But their mandate also extends to crucial technical and historical symbols. They recognize that the ISO 2047 visual representations, while no longer used for daily debugging, are a fundamental part of computing history. They are the hieroglyphs of the digital age.
So where do they live in the Unicode table?
The ISO 2047 symbols for control characters are specifically mapped and cited in 2 Unicode ranges. First, the miscellaneous technical block, which spans hexadecimal codes 2300 through 23FF. Here you'll find things like the empty box for null and the literal bell symbol for BEL. But more specifically, there's a dedicated block called control pictures, ranging from hex 2400 to 243F.
Control pictures. I love that phrase. It sounds like a wing in a modern art museum.
Functionally, it is a digital museum. That block contains specialized diagonal acronym graphics designed to represent the control codes if a system absolutely needs to display them, preserving the intent of ISO 2047 in a modern typographic format. So while a programmer at a tech startup today will never use ISO 2047 to debug a cloud microservice, the foundational visual language designed by that committee in 1975 has been permanently etched into the master dictionary of human communication. It will exist as long as Unicode exists, which is to say, as long as our current digital civilization endures.
That is a staggering thought. Let's take a step back and look at the whole picture. What an incredible, unexpected journey from a single, dry Wikipedia table. We started this deep dive looking at what seemed like an impenetrable list of 1970s hex codes and bureaucratic acronyms. But by digging in, by looking closely at what those codes actually represented, we discovered a vibrant, noisy, intensely physical world. We found heavy steel machines physically ringing bells to demand human attention. We found mechanical paper tape punches violently tearing holes in paper to record data. We found isolated terminals interrogating each other across crackling telephone lines, mechanically spinning drums to ask, "Who are you?" We saw the monumental, agonizing international effort to take invisible data commands and force them into visible graphical shapes, just so human engineers could peer into the dark and understand what the machines were saying to each other.
It really exposes the hidden physical architecture that underlies the smooth, abstract digital world we inhabit today. Every sleek interface is built on a foundation of these crude physical negotiations.
It absolutely is. And it fundamentally changes how you look at the device sitting in front of you right now. The next time you, the listener, are typing an email and you hit the Enter key, I want you to remember that you aren't just moving a pixelated cursor down a screen. You are invoking a carriage return and a line feed, the ghost of a heavy metal cylinder slamming to the left, and a rubber roller ratcheting paper upward. When you press the S key in the corner of your keyboard, you are triggering a command designed 50 years ago to break a terminal out of a 7-bit prison. You are participating in a lineage of commands that stretches back through clattering teletype machines, across international standards committees in 1968, all the way to the foundational logic of the digital age.
That historical continuity is profound, and it raises a final provocative thought that I'd like to leave our listener with today. We have spent this entire session looking backward. We've examined the invisible control commands of the 1970s and the immense creative effort required to visualize them for human comprehension. But let's apply that logic to the future.
Okay, let's spin it forward.
If some future historian or digital archaeologist were to dig through the raw foundational code of the systems we use right now in the 2020s, long after our current screens, laptops, and interfaces have turned to dust, what invisible control commands of our modern era do you think they would struggle to visualize? We aren't just dealing with line feeds and paper tape anymore. We are dealing with massive neural networks, opaque algorithmic weighting, and decentralized cloud infrastructures.
That's a huge question. What is the modern equivalent of a carriage return?
Exactly. What new, bizarre symbols would a future committee have to invent to visualize the invisible forces of today? How do you draw a static picture of a command that subtly adjusts a machine learning algorithm's bias? How do you graphically represent a protocol that silently trades a fraction of a cent on a high-frequency stock market in a microsecond? What would those new symbols look like, and more importantly, what would they say about what our society values and controls today?
How do you draw the invisible forces of the 21st century? That is a brilliant question, something deep to mull over the next time you stare at a blinking cursor on a blank screen. Thank you so much for joining us on this incredibly detailed journey through the hidden logic of ISO 2047. Keep questioning the invisible structures around you, and we will catch you on the next deep dive.